There's a moment on an Antarctic survey flight that nobody bothers to film because there's nothing to see. The aircraft is holding a straight line at a few thousand feet over the East Antarctic Plateau. Out the window, white. Not interesting white, not photogenic white. Flat, sunlit, featureless white that runs to the horizon in every direction and gives the eye absolutely nothing to hold on to. The pilots fly on instruments. The scientists in the back have their eyes on a screen. Under the belly of the plane, an antenna is firing radio pulses down into the ice, one after another, thousands of times a minute. Each pulse travels down through the ice sheet, hits whatever is at the bottom, and bounces back up. The instrument measures how long the round trip took. From that number, and from how fast radio waves travel through cold ice, you get a depth. Do that a few million times along a straight line, and you get a cross-section of the continent, a profile of the land under 2 miles of ice that no human eye will ever look at. That's how we know the shape of Antarctica, not by seeing it, by listening to an echo and doing arithmetic. Now here's the part that changes how you should read every map of that continent you've ever seen. The echo only tells you about the ground directly beneath the aircraft. A survey flight is a line. A line has no width. Fly another line 15 miles away, and you have 2 profiles with 15 miles of nothing in between, and that nothing has to be filled in by somebody, using a computer, using assumptions about how landscapes usually behave. In March of 2025, a consortium of research institutions published BedMap 3, the newest and most complete picture of the rock beneath the Antarctic ice sheet. It pulled together more than 6 decades of surveys flown by aircraft, dragged by tractors, and in the earliest days hauled behind dog sleds. It added 52 million new measurement points that BedMap 2 never had, and well over 1 million miles of new survey line. It's the best map of that landscape that has ever existed by a wide margin, and the people who built it are careful and honest about what it is. And in the deep interior of East Antarctica, there are still places on that map where the nearest actual measurement is more than 60 miles away, and the mountains and valleys you see drawn in between are an interpolation, a plausible guess, a shape that a mathematical routine produced because it had to produce something, and because leaving a hole in the middle of a continent isn't an option when the map has to feed a climate model. Let me be exact here, because this gets exaggerated in both directions. It is not that we know nothing about Antarctica. We know an enormous amount, and the amount grows every field season. It's that the word people reach for when they talk about this place, unexplained, is quietly doing at least 6 completely different jobs, and lumping them together is what turns real science into rumor. Something can be unexplained because nobody has ever measured it. That's a hole in the map, and it's fixable with a survey, aircraft, and money. Something can be unexplained because it has been measured, but not often enough, or not in the right season, or at 14 points across an area the size of the United States and Mexico combined. That's a sampling problem, and it produces confident-looking maps built on almost nothing. Something can be unexplained because we have excellent data about it and have never laid eyes on it. Sonar knows it's there. Radar knows it's there. No camera has ever been in the room. Something can be unexplained because we know precisely where to go and cannot physically get there. Not for lack of will, but because the machine that would do the job doesn't exist yet or costs more than the entire national polar budget. Something can be unexplained because 2 groups of serious researchers are looking at the same dataset and reaching incompatible conclusions, and neither one is being unreasonable. And something can be unexplained in the oldest and purest sense. The observation is solid, it's been repeated, nobody disputes it, and there's no accepted mechanism that accounts for it. 6 different kinds of missing. 20 specific places, features, and measurements in Antarctica and the Southern Ocean that sit in one of those 6 categories right now in the current published literature, sorted by which kind of missing they are. A word about what you won't find here. No lost civilizations under the ice, no secret installations, no paranormal anything. Antarctica attracts that stuff the way a magnet attracts filings, and every time somebody dresses up a legitimate geophysical puzzle in a cape, the actual puzzle gets buried under it, which is a shame, because the actual puzzles are better. Where one of the famous Antarctic mysteries turns out to be a solved question wearing a rumor as a disguise, I'll say so plainly, and then show you the real question underneath. Because in most of those cases, there's a real question underneath, and it's usually more interesting than the story that got attached to it. Start with the simplest kind of not knowing, the kind where the measurement was never taken at all. There are 3 of these, and they're all about shape. Not about what something does, or why it behaves the way it does, about what it looks like. The physical geometry of a piece of the Earth, which sounds like the most basic thing a geographer could possibly want, and which in Antarctica is often the thing we're least sure of. The first one is the map itself. Antarctica covers about 5.4 million square miles. More than 99% of that is buried under ice, and the ice averages well over a mile thick, running to nearly 3 miles in the deepest basins. A study using satellite imagery put the total area of exposed bare rock on the entire continent at about 8,400 square miles, 0.2%. That's the whole of the rock geologists can walk up to and hit with a hammer. Everything else, the mountain ranges, the canyons, the plains, the coastline of the actual land as opposed to the coastline of the ice, is known only through remote sensing. So the question of what Antarctica physically looks like under its cover gets answered by echo, by gravity, by magnetics, and by a great deal of careful inference. Going and looking is off the table. BedMap 3 is the current answer. Strip the ice away in your head, and here's what it shows you. East Antarctica is a big, ancient, mostly high continental block, with mountain ranges buried under thousands of feet of ice and deep troughs cut into its margins. West Antarctica is a different animal entirely, an archipelago, essentially, a scatter of islands and highlands connected by ice, with vast areas of bedrock sitting well below sea level. If the ice vanished tomorrow and the sea rushed in, West Antarctica would be an island chain. That's not speculation. That's what the radar returns say. And within that map, the coverage is wildly uneven. Around the coasts, along the big glaciers, in the places where sea level rise research is concentrated, the survey lines are dense, and the picture is good. Fly inland, and the lines thin out. Fly into the middle of the East Antarctic Plateau, and you're in the emptiest surveyed space on the planet's surface. The reason is not mystery, it's logistics. A survey aircraft has a range. It needs fuel. And fuel in interior Antarctica has to be flown in, one drum at a time, and cached at a depot that somebody has to establish first. Every hour of survey line over the deep interior costs a fortune in aviation fuel that had to be shipped to the coast, moved inland by traverse, and stored. The blank spaces on the bed map exist because a gallon of jet fuel at 80 degrees south is about the most expensive substance a scientific budget can buy, which produces a strange consequence that I find quietly unsettling when I think about it too long. The published bed map has no visible seams. It's a smooth, continuous, beautifully rendered surface, and it looks equally authoritative everywhere. The uncertainty is real, and the people who made it document it carefully in the accompanying data, with error estimates that balloon in the sparse regions. But the picture itself doesn't warn you. A mountain in a well-surveyed area and a mountain in a blank corridor look exactly the same on screen, and only one of them has been measured. Here's the piece of this that best shows how live the question still is. For years, the thickest ice in Antarctica was thought to sit in the Astrolabe Basin, in a daily land. BedMap 3 reinterpreted the data and moved it. The thickest ice we currently know about is in an unnamed canyon in Wilkes Land, at roughly 76 degrees south and 118 degrees east, where the current best estimate puts the ice at close to 15,600 feet. Nearly 3 miles of ice, stacked in a valley with no name, and the record moved because somebody looked again at numbers that were already sitting in the archive. Think about what that implies. The deepest ice on Earth changed address inside a single publication cycle, and no new field data was involved. The analysis simply improved, which means the current answer is provisional too. There are canyons in the unsurveyed corridors that have never had a radar pulse land in them. Some of them are almost certainly deeper. So what would actually close this gap? Nothing exotic. More flight lines, flown at tighter spacing, over the interior, autonomous long-range aircraft that don't need a human crew or a heated cabin would drop the cost per mile enormously. And several groups are working on exactly that. Satellite radar can't do it, because the frequencies that penetrate ice don't work well from orbit, and the ones that work from orbit don't penetrate ice. It's a flying problem, and it's solvable. And the reason it isn't solved is that solving it requires several $100 million nobody has allocated. That's the first unknown, and notice its character. There's no mystery in it at all in the spooky sense. It's a purchasing decision that hasn't been made, which is exactly why the deep interior of the East Antarctic bed is going to stay a drawing for a while longer. The second unknown of shape is a hole in that same map, and it's the deepest one on the planet. Somewhere in East Antarctica, in a stretch of coast most people have never heard of, there's a valley in the bedrock that goes down about 11,500 feet below sea level, 2.2 miles below the surface of the ocean, cut into continental rock on land. It's called the Denman Trough, and it holds the Denman Glacier, and it is the deepest point on any landmass on Earth. Not the deepest point in the ocean, which is the Challenger Deep and is roughly 3 times deeper. The deepest point on land, the lowest place on the planet where you're standing on a continent rather than on ocean floor. The Dead Sea shore, which is what most people think of, sits about 1,400 feet below sea level. The Denman Trough beats it by a factor of 8, and the only reason it isn't full of seawater is that it's plugged with ice. The trough is roughly 60 miles long and about a dozen miles wide, a narrow slot in the bedrock with the glacier packed into it like a cork in the neck of a bottle. And the reason it belongs in the category of things nobody has measured properly is a lovely piece of physics that defeated everyone who tried. Ice-penetrating radar works by timing an echo off the bottom. That works beautifully when the bottom is a broad, flat surface, because the strongest return comes straight up from directly below you. The Denman Trough is a deep, steep-sided canyon. Fly a radar aircraft along it, and the pulse doesn't just go down, it spreads. It hits the canyon walls on both sides, which are much closer to the aircraft than the canyon floor is. And those side echoes come back first and come back stronger. The floor's echo, the one you actually want, arrives late and weak and gets buried in the clutter from the walls. Survey after survey went over the Denman and came back without a bed. The instrument had worked perfectly. The valley was simply shaped in a way that made the instrument useless, so the depth we have came out of a calculation. In 2019, a team led by glaciologists at the University of California, Irvine published a map called Bed Machine Antarctica, built on a different approach. Instead of relying on the echo, they used mass conservation. Satellites can measure how fast the ice at the surface is moving, very precisely, and they can measure how much snow falls on it and how much it thins. If you know how much ice is moving through a given cross-section per year, and you know how fast it's going, then arithmetic gives you the cross-sectional area it must be flowing through, which gives you the shape of the channel, without ever getting an echo off the bottom of it. That's how the deepest place on land was found, not by sounding it. By working out how much room the ice needed in order to move the way the satellites saw it moving. I have a lot of respect for that method, and its status should be stated plainly. It's an inference. A very well-constrained one, built on data from 19 research institutions and more than 40 years of observations, and it produces results that match direct radar measurements closely in the places where both exist. But the Denman Trough is precisely the place where direct radar doesn't exist. The 11,500 feet is the number that makes the ice flow work out. Nobody has bounced a signal off that valley floor and gotten a clean return. And the reason this matters beyond the trivia value, a trough that deep, connected to the ocean, is a ramp. Warm ocean water sitting at depth on the continental shelf can flow inland along a bed that slopes downward, and the further it goes, the more ice it can undercut. Denman has been retreating. Between the 1990s and the late 2010s, its grounding line, the boundary where the glacier stops resting on rock and starts floating on seawater, moved back roughly 3 miles on the western flank. The eastern flank held, apparently because of a ridge in the bedrock. And whether that ridge holds, and how far back the trough deepens before it shallows again, depends entirely on a bed shape that we currently have by calculation, rather than by sounding. Denman alone holds enough ice to raise global sea level by about 5 feet. It's one glacier in a part of East Antarctica that used to be filed under stable and no longer is. What would settle it? Seismic surveys on the ice surface, which use a physical shock rather than a radio pulse and don't suffer the same side echo problem, could get a direct bed depth. That means putting a traverse team on the glacier for a season with explosives or a vibrating source, which is expensive and slow but entirely possible. Nobody has done it across the trough. Until somebody does, the deepest point on land is a number that came out of a calculation. And the honest uncertainty on it is measured in hundreds of feet. The third gap in shape is the one I'd argue matters most for anyone who lives near a coastline. And it's the least visible of all, because it's a room with the lights off and no way in. Antarctica's ice doesn't stop at the shore. It flows off the land and out over the water, and it keeps floating in enormous slabs called ice shelves. The Ross Ice Shelf is the biggest. It covers close to 200,000 square miles, which is more than California, and it floats on the Ross Sea with its surface 100 or so feet above the waterline and its base hundreds of feet below. Underneath it is a sealed body of seawater the size of a large country, permanently roofed with ice, permanently dark, connected to the open ocean only along its outer edge. Everything that happens to that ice shelf from below happens in that room. Warm water that gets in there melts the underside. Cold, dense water that forms in there sinks and flows out. The rate at which the Ross Ice Shelf thins or thickens, and therefore how well it keeps buttressing the glaciers behind it, is controlled by how water circulates in a space nobody can enter. And the circulation depends, more than anything else, on the shape of the seafloor down there, where the ridges are, where the deep channels run, whether a trough connects the open ocean to the deep interior of the cavity, or gets blocked by a sill halfway. A sill a few hundred feet high in the right place can keep warm water out of an entire embayment. Move that sill 200 feet down, and the same embayment starts melting from beneath. We do not have that map. What we have is a series of approximations. The first proper survey of the Ross Ice Shelf, in the 1970s, worked on a grid with points spaced about 35 miles apart. 35 miles. Imagine mapping the terrain of Colorado by taking one elevation, reading every 35 miles, and drawing the mountains in between. The Rosetta Project, flying in 2015 through 2017, tightened that to roughly 6 to 12 miles in the areas it covered, using airborne gravity to infer the seafloor depth, because gravity is sensitive to how much rock versus how much water is underneath you. And radar can't see through seawater at all. A circumpolar effort published in 2024 produced the first full bathymetry of every Antarctic ice shelf cavity, and it did it the same way. A three-dimensional inversion of gravity anomalies, constrained wherever real depth soundings happen to exist. It's a serious piece of work, and it's the best thing available. It is also, by construction, a model of the seafloor rather than a survey of it. The direct measurements that do exist come from an almost absurdly narrow set of access points. You can melt a hole through the shelf with a hot water drill, which takes days, produces an opening maybe a foot or two across, and gives you one column of information at one spot. There have been a few dozen such holes in the history of Antarctic science, spread across shelves that together cover an area larger than Alaska and Texas combined. Some of the best data comes from robotic submersibles sent through those holes, which can range a few miles from the borehole before they have to turn around because the tether has a length and the vehicle has to come back to the same small hole it went in through. Add it up, and here's the shape of what's missing. The cavity beneath the world's largest ice shelf, the room whose geometry determines how fast the ice above it melts, has been physically sounded along a tiny fraction of its extent. The rest is a gravity inversion with error bars that are rarely printed on the pretty version of the map. If you want to see what that ignorance costs, look at what happened to the Larsen B ice shelf on the Antarctic Peninsula in 2002. It had been there through the entire Holocene, roughly 12,000 years, and over about 5 weeks it disintegrated into a slurry of icebergs. Around 1,200 square miles of floating ice, gone in a month and a half. The immediate trigger was surface meltwater draining into crevasses and wedging them open, which is a mechanism operating from above rather than below, and it was recognized quickly. What the collapse also demonstrated, and what changed the field permanently, is what happened next. The glaciers that had been feeding Larsen B accelerated, some of them by a factor of several, within a year. The shelf had been a break. Nobody had fully believed how strong a break until it was removed. Ever since, the central question about every remaining Antarctic ice shelf is how much longer it can hold. And the ocean side of that question runs entirely through the cavity underneath. Whether warm water can get in, which channel it uses, where it strikes the ice. And that is the map we're drawing from gravity. There's a variation of this problem that deserves its own mention because it applies to the whole rim of the continent. The troughs cutting across the Antarctic continental shelf, the ones that deliver warm, deep water to the glacier fronts in the first place, are themselves poorly surveyed. They were carved by Yar ice streams during past glacial maxima, so they run inland, and their depth and their sill heights decide whether a given glacier gets warm water or does not. A great many of them have never had a ship pass over with a multi-beam sonar running, because ships go where the science stations and the shipping lanes are, and Antarctic shipping lanes are short. The measurement that would move this is not mysterious either. Autonomous underwater vehicles that can navigate for hundreds of miles under ice without a tether, mapping the cavity roof and floor as they go, and find their own way back out. Prototypes exist. Several have made long runs under Antarctic ice and come home. Scaling that up to a systematic survey of an area the size of Spain, under a roof that will kill the vehicle if it surfaces in the wrong place, is a hard engineering problem that will probably be solved in the next decade or two. Right now, the floor of the largest sealed sea on Earth is drawn from the pull of gravity on an airplane flying overhead. Those are the three shape problems. Notice what they share. In all three, the missing thing is geometry, and in all three, the fix is a survey somebody hasn't paid for yet. The next four are different. In these, the measurement has been taken. It has just been taken so rarely, or in such a narrow window, that the confidence people place in the result is running far ahead of the data underneath it. Start with the one that quietly poisons everything downstream of it. How much heat is coming up out of the rock? Every point on the Earth's surface leaks a little heat from below. It comes from radioactive decay in the crust and from the slow cooling of the deep interior, and on a continent, it's usually a trickle. In most places, it makes no practical difference to anything. You'd never notice it. Stand on a granite outcrop in Vermont, and the heat rising into your boots from 4 billion years of planetary cooling is a rounding error compared with the sun. Put 2 miles of ice on top of that same outcrop, and it stops being a rounding error. It becomes the single thing that decides whether the bottom of the ice sheet is frozen solid to the rock or sitting in a film of meltwater. That distinction is not subtle. Ice frozen to bedrock barely moves. Ice sitting on water slides. The difference in flow speed between a glacier bed that's frozen and a glacier bed that's lubricated can be a factor of 100 or more. Whether West Antarctica dumps its ice into the ocean over 3 centuries or over 3,000 years depends heavily on which of those two conditions the bed is in and where the boundary between them runs. So, how much heat is coming up under the Antarctic ice sheet? The honest answer is that we have somewhere around 12 direct measurements for a continent larger than the contiguous United States and Mexico put together. And the models built to fill in the gaps disagree with each other by more than a factor of 2. And where the direct measurements land, they tend to be higher than the models predicted. To get a direct number, you need a deep hole in the ice with a temperature sensor in it, and you need to measure the temperature gradient near the bottom. And then you need to correct for the fact that ice flows, that it deforms and generates its own frictional heat, and that surface temperatures over the last glacial cycle were different from today's, and that signal is still working its way down through the ice column. It's delicate work. Only a handful of boreholes go deep enough. An analysis published in 2020 of temperature profiles from those deep holes gave numbers like this. At Dome C on the East Antarctic Plateau, about 58 milliwatts per square meter. At Dome Fuji, about 79. At the Conan site, about 87. And in a separate treatment of the same site, considerably higher again. And at the West Antarctic Ice Sheet Divide, the analysis produced a figure north of 250, which sits several times above what the regional models expected. Every one of those came out above what the continental scale models had predicted for that spot. There are perfectly ordinary explanations available. Extra radioactive heat in unusually enriched crust, hot water circulating in the rock beneath the ice, moving heat around in ways a smooth model can't capture, local volcanic influence in West Antarctica, which sits on an active rift. And the deconvolution problem is real. Separating the geothermal signal from the ice sheet's own thermal history is difficult enough that reasonable people get different answers from the same borehole. But look at the situation from a distance. The maps of Antarctic geothermal heat flux that get fed into ice sheet models are built almost entirely from indirect proxies. Magnetic data, which senses the depth at which rock loses its magnetism, and therefore hints at temperature. Seismic data, which senses how rigid the mantle is underneath. Both of those give you a smooth continent-scale field, with resolution measured in tens or hundreds of miles. Neither one can see a hot patch 15 miles across sitting under an ice stream, and the ground truth available to check those maps against is under 20 points. There's a related discovery from 2025 that shows how thin the seismic picture underneath is. Researchers use deep learning to comb through recordings from 49 seismic stations across East Antarctica, hunting for signals too small or too messy for conventional detection to catch. They found over 500 earthquakes at intermediate depth down in the upper mantle, under a continental interior that was assumed for most of a century to be about as seismically quiet as a place can get. Antarctica's reputation as an aseismic continent turns out to have been substantially a detection artifact. Nobody had enough seismometers on the ice, running long enough to see what was there. Put more instruments out, apply better processing, and the quiet continent starts talking. That doesn't overturn the geology, and nobody is suggesting Antarctica is a hazard zone. It does tell you something uncomfortable about every other statement of the form. Antarctica does not have much of X. Some of those statements are about Antarctica. Some of them are about how few instruments we've put on it. So the exact boundary on this one? We know the average heat flux under Antarctica to something like a factor of 2. We know it's spatially variable in ways the maps can't resolve. And the ice sheet models that project sea level rise for the next few centuries take that field as an input. What would move it is straightforward and tedious, more deep boreholes, with proper thermal instrumentation distributed across the continent rather than clustered where the ice core projects happen to want ancient air, plus a denser seismic network left running for years rather than a season. Each hole is a multi-year project. There's no shortcut, which leads directly to the next one, because that heat, wherever it's coming from, is doing something. It's melting the bottom of the ice sheet, and that meltwater goes somewhere. Under the Antarctic ice sheet there is water, not a trickle. Lakes. The first hints came in the 1960s and 70s, from Soviet and British radar flights that kept picking up a return from the base of the ice that was too bright, too flat, too mirror-like to be rock. Water reflects radio waves far more strongly than rock does, and a smooth horizontal reflector at the bottom of the ice sheet means a body of standing water. The count has been climbing ever since. A global inventory published in 2022 cataloged 675 subglacial lakes in Antarctica, 59 of which were new in that paper alone. More than 130 of them are classified as active, meaning they fill and drain. That word active deserves a moment because it's the part that turns a static curiosity into a system. Here's how you detect it, and the technique is a lovely piece of orbital cleverness. Satellite altimeters measure the elevation of the ice surface to within inches. If a lake 10 miles wide under 2 miles of ice slowly drains, the ice above it sags, because it has lost the water it was floating on. The surface drops by a few feet over a couple of years, in an oval patch, and then rises again as the lake refills. From orbit, you watch a patch of featureless white plateau breathe in and out, and from that, you deduce a lake the size of a city emptying and refilling beneath it. And when one lake drains, the water has to go somewhere. In several documented cases, a lake drained, and months later, a lake downstream rose. Then another one below that. The pulse propagates. The subglacial lakes form a connected drainage system, with rivers running between them, under 2 miles of ice, powered by geothermal heat from below and friction from the sliding ice above, and organized by the pressure of the ice rather than by gravity alone, which means it can and does run uphill. The Recovery Lakes, a chain of 4 large lakes in East Antarctica, Siurwar Kwar Sankshinkastinj, sit at the head of the Recovery Glacier, which drains a substantial slice of the East Antarctic ice sheet. The consensus interpretation is that the water in and around those lakes is a large part of why that glacier flows as fast as it does and why fast flow begins where it does. Change the water, and you change the glacier. Now, the missing part, we have detected 675 lakes and mapped a plumbing system connecting some of them, essentially entirely by inference from the surface. And human beings have put an instrument into exactly 3 of them. Lake Whillans in West Antarctica was cleanly entered in 2013 by an American team using a filtered, ultraviolet-treated hot water drill, and it came up with a thriving microbial ecosystem living on chemical energy in permanent darkness. Lake Mercer, nearby, was entered in 2018 by the same lineage of project. And Lake Vostok was penetrated in 2012, in a way that generated a decade of argument and that I'll come back to. 3 out of 675. And 2 of the 3 are shallow, sediment-floored lakes under fast-moving ice in West Antarctica, which is not remotely representative of the deep, ancient, isolated lakes of the East Antarctic interior. There was very nearly a 4th, and the way it failed tells you what this work actually involves. Lake Ellsworth sits under about 2 miles of ice in West Antarctica, in a deep subglacial valley. And it was chosen for a British attempt because it looked like the best combination of scientific interest and reachable logistics. The equipment was designed over years. Around 70 tons of gear went to the site, including a hot water drill built specifically for the job and a probe carrying a full suite of instruments and sterile sample chambers. In December of 2012, they started melting downward. The plan required 2 holes, one main borehole to the lake, and a second cavity melted alongside it, filled with meltwater to act as a reservoir, supplying the drill as it went deeper. The two had to link up underground. They did not. The drill could not establish the connection. Fuel for the boilers was being consumed at the rate the operation demanded, and the team was running out of the season. After several days of trying, with the weather closing and the fuel margin gone, they called it off. 12 years of preparation, an enormous logistical effort, and no hole. The project has not been repeated. I mention it because there's a temptation, looking at a list of unknowns like this, to assume the gaps persist because nobody has gotten around to them. Some of them persist because people put a decade of their careers into closing one and the ice said no. There's a second layer of missing here too, and it's the one that makes glaciologists uneasy. The inventory itself is biased by where the survey lines are. A lake shows up as a bright, flat radar reflector, and you only see it if an aircraft flew over it. Go back to the blank corridors in the interior bed map, the ones 60 miles from the nearest measurement, and ask how many lakes are sitting in them. The honest answer is that nobody knows, and the number is not small. Estimates of how many Antarctic subglacial lakes remain undetected run into the hundreds. So the state of knowledge is this. There's a continent-sized hydrological system under the ice. We can watch parts of it move from orbit. We have sampled 3 points in it, and we don't know how many components it has. The measurement that would change it is a clean access hole into a deep interior East Antarctic lake, which requires a drilling campaign at a site hundreds of miles from any station, and a sterilization protocol strict enough to satisfy an international treaty. Because contaminating a body of water that has been isolated for hundreds of thousands of years is a thing you get exactly one chance to avoid. Now take the lakes and the rivers between them and ask an obvious question that almost nobody asked for 50 years. What's underneath the water? Not underneath the ice, underneath the subglacial lakes. Below the film of meltwater at the base of the ice sheet, there's sediment. Layers of ground-up rock, sand, and clay, deposited over millions of years by glaciers advancing and retreating, and by seas that came and went. And sediment, anywhere else on Earth, holds groundwater. In 2022, a team went out onto the Whillans ice stream in West Antarctica with a technique that hadn't been used this way in Antarctica before: magnetotellurics. The principle is elegant. The Earth is constantly bathed in natural electromagnetic variation, generated by the solar wind hitting the magnetosphere and by lightning storms in the tropics. Those fields penetrate the ground. How deeply they penetrate and how they're distorted depends on how electrically conductive the material is. Salty water conducts extremely well. Dry rock conducts poorly. Set up instruments on the surface. Listen for weeks, and you can build a profile of electrical conductivity going down through the ice, through the sediment, into the crust. What they found under Whillans was a layer of sediment between about 1,600 and 6,000 feet thick, and it was saturated. Not damp. Saturated with water that got saltier with depth, reaching roughly seawater salinity a few thousand feet down. The volume estimate is the part that stops you. The groundwater in that sediment column holds something like 10 times as much water as the entire shallow system above it. All the lakes, all the subglacial rivers, all the films of meltwater at the ice base, added together, are a tenth of what's sitting in the sediment underneath them, and it's not sealed off. The measurements suggest the deep groundwater exchanges with the shallow system. Water moves between them. The origin story reads like a piece of geological archaeology. The salt is old seawater. During warmer intervals, the ocean flooded into what's now West Antarctica, laid down marine sediment saturated with seawater, and then the ice came back and sealed it in. Radiocarbon in the upper sediments suggests most of the salty water in the shallower part of the system arrived within the last 10,000 years, which puts it in the window since the last glacial maximum, when the grounding line was much further out, and the sea was where the ice is now, so there's a reservoir of fossil seawater, deeper than a mountain is tall, sitting under the ice streams of West Antarctica, connected to the water that lubricates them. Why does that matter? Because groundwater does two things that change how an ice stream behaves. It buffers. If the shallow drainage system loses water, groundwater can feed back into it, which means the bed might stay lubricated during periods when nothing is melting. And it stores heat and salt, which affects the freezing point at the bed and how the sediment deforms under load. Ice streams don't only slide on water. They also ride on soft, deforming sediment. And how soft that sediment is depends on its pore water pressure, which is a groundwater question. Essentially, every ice sheet model in use treats the bed as a two-dimensional surface with a water film on it. This says the bed is a three-dimensional volume with a reservoir in it. Here's the state of the evidence. One field campaign, one ice stream, two sites within it. The technique is sound, and the interpretation is careful, and the authors themselves flag that they have no idea whether this is a local peculiarity of Whillans or a general property of the West Antarctic bed, whether the Thwaites bed holds the same thing, or the Pine Island bed, or the East Antarctic interior is unmeasured. What would move it? Magnetotelluric surveys are relatively cheap by Antarctic standards. Instruments, a season, a small team. Doing a dozen of them across West Antarctica would tell you whether this is a system or an anomaly, and that work has begun. The unknown right now is whether it's everywhere, and how fast it moves, and neither of those has been measured at a second location. The fourth sampling problem is the largest and the most stubborn, and it comes down to a season nobody works in. The Southern Ocean is the ring of water that circles Antarctica with no continent to interrupt it. It's the only ocean on Earth that runs all the way around the planet, and the current that runs through it, the Antarctic Circumpolar Current, moves more water than any other current on the planet by a wide margin. What happens in that ring sets the temperature of the deep ocean everywhere else. It's the engine room. And through the southern winter from roughly April to October, it's effectively unobservable at the surface. The sea ice closes over it. At maximum extent, sea ice covers something like 7 million square miles of the Southern Ocean, an area roughly twice the size of the entire United States. And it does that in about 6 months, and then melts most of it away again. That's the largest seasonal change of any physical feature on the surface of this planet. Nothing else moves that much material that fast. Ships mostly cannot go in. Research vessels that work in the Antarctic summer are not in the business of being frozen into pack ice in 24-hour darkness in 80-knot winds. And the icebreakers capable of it have other jobs, and their operators are extremely reluctant. So the winter Southern Ocean is sampled by three things: satellites, which see the top of the ice and not the water under it, autonomous floats that drift and dive and surface, and instrumented seals. That last one is not a joke. Elephant seals and Weddell seals are fitted with small satellite tags that record temperature and salinity as the animal dives. Those animals go under the ice, dive to depths of several thousand feet, and surface at breathing holes, transmitting profiles that no ship could have collected. A meaningful share of what oceanographers know about the winter water column beneath Antarctic sea ice was collected by seals doing their ordinary business. That's ingenious. And it's also a reminder of how far we are from a systematic observation. The seals go where the seals go. The floats drift where the current takes them and can get trapped under ice. There is no winter grid, so here's the specific hole in that map, and it's a literal one. Out in the Weddell Sea, well south of the ice edge, there's an underwater mountain called Maud Rise. It sits about a mile below the surface, a broad seamount in the middle of deep water. And in the winters of 1974, 75, and 76, satellite images showed something that should not have been there. An enormous patch of open water in the middle of the winter sea ice, right over Maud Rise. At its peak, it reached roughly 100,000 square miles of open ocean in the middle of winter, hundreds of miles from the ice edge, in air temperatures that should have frozen it over in days. An open water area inside sea ice is called a polynya. Coastal ones are common and well understood. Wind blows the ice away from the shore, and new ice forms in the gap. An open ocean polynya of that size, that far from land, sustained through consecutive winters, is a different beast. It means water from below, warm enough and salty enough, was being brought up to the surface fast enough to melt the ice as fast as it formed, all winter, over an area the size of Colorado. Then in 1977, it closed, and it stayed closed for 40 years. In 2016, it came back, briefly. In 2017, it came back properly, opening to something like 30,000 square miles, roughly the size of South Carolina. And this time there were floats in the water, and satellites overhead with capabilities the 1970s could not have imagined. The explanation that has emerged is a chain, and every link of it is real physics. Deep in the Weddell Sea, below a few hundred feet, there's a layer of relatively warm, salty water. It stays down there because the water above it is colder but fresher, and fresh water is buoyant, so the column is stable and the heat stays trapped. Maud Rise sticks up into that layer and disturbs the flow around it, creating a rotating structure, a kind of standing eddy sitting over the seamount. Storms passing through drive the surface ice and water, and the rotation of the Earth turns that push sideways. A process called Ekman transport, which shoves salt across the current that girdles the northern flank of the rise. Add salt at the surface, and the surface water gets denser. Denser surface water sinks. Sinking surface water is replaced by the warm water from below. That warm water melts ice. Melting ice adds fresh water, which should shut the whole thing down except that the salt transport keeps replacing it. That's a 2024 result, and it's a serious advance. Several outlets reported it as the 50-year mystery being solved. I'd put it a notch lower than solved. And so, more carefully, do the people who published it. What that work establishes is a mechanism that can produce the polynya and that matches the 2017 observations well. What it doesn't establish is the prediction. Nobody can currently tell you which winters the Maud Rise polynya will open in. The preconditions involve the strength of the deep warm layer, which builds up over years or decades, and the storm track, which varies, and the state of the eddy, which nobody watches continuously. 40 years passed between appearances. There's no accepted account of what took it 40 years, and no forecast for the next one. And I'll note the obvious, since Maud Rise is a favorite of a certain kind of internet content. A large hole in Antarctic sea ice is open sea surface, and nothing else. What makes it worth your attention is that it represents an enormous release of heat from the deep ocean straight to the atmosphere, in a place where that heat was supposed to stay locked away for centuries, and we cannot predict when it will happen again. The unresolved boundary on the winter Southern Ocean in general. We have a physical mechanism for the polynya, no ability to forecast it, and a winter ocean whose subsurface structure is known from drifting floats and diving mammals, rather than from any planned survey. The measurement that would change it is a network of ice-capable, autonomous floats and moorings, deployed in the Weddell Gyre and left through multiple winters, reporting under the ice. Programs to do that are underway and are far from complete. 4 sampling problems, and a pattern across all of them. In each case, the data exists, and the data is good, and there's simply not enough of it in space or in time to support the confidence that the resulting maps project. That's a different failure from having no data at all, and in some ways it's more dangerous, because sparse data produces smooth pictures, and smooth pictures look finished. The next 3 unknowns are stranger, because in these cases we have plenty of data. What we have never had is a look. 2 1/3 miles under Vostok Station, in the coldest place ever recorded on the surface of this planet, there's a lake about 160 miles long. Lake Vostok is the largest of the Antarctic subglacial lakes by a huge margin. It's roughly the size of Lake Ontario in surface area, deeper than Lake Ontario in places, and it has been sealed under the ice sheet for a length of time that gets argued about but is measured in millions of years. The water in it is liquid because the weight of the ice above lowers the freezing point, and because heat from the rock below keeps it from giving up. We know the shape of it from radar and seismic surveys. And we know something about its interior circulation from modeling, and we know from satellite altimetry that the ice above it behaves like ice floating on water because it does the things floating ice does. There's a well-documented magnetic anomaly over part of the lake, picked up by airborne magnetometers, which for a while got recycled online into claims about buried structures and hidden installations. The mainstream geophysical reading is unremarkable. The rock beneath the lake basin differs in composition from the rock around it, which is exactly what you'd expect at a tectonic boundary, and the anomaly maps onto a plausible geological contact. It's rock chemistry, not architecture. What nobody has, after 50 years of studying it, is a sample of the water. That claim needs a careful qualifier, because a great many people believe the lake was sampled in 2012. And something did happen in 2012. The Soviet and then Russian program at Vostok had been drilling downward since the 1970s, originally for climate records rather than for the lake, which nobody had confirmed existed until the 1990s. By the time the lake was confirmed, the borehole was already thousands of feet deep, and it was being kept open the way deep ice boreholes were kept open in that era, filled with kerosene and freon, to balance the pressure of the ice, which would otherwise squeeze the hole shut, which created the problem. You have a borehole descending toward a body of water that has been isolated from the atmosphere for millions of years, and the hole is full of aviation fuel. Drilling stopped for years, while the international community argued about it. A protocol was eventually agreed and modified. The plan was to stop short of the water, let the final push be made in a way that the lake's own pressure would drive water up into the hole rather than letting drill fluid go down into the lake, and sample the water after it refroze. On the 6th of February 2012, at a depth of about 12,370 feet, the drill reached the water. Lake water rose several hundred feet up the borehole and froze there. The following season, that refrozen water was cored and analyzed. So what came out of that analysis was water that had risen into a kerosene-filled hole, mixed to an unknown degree with the drill fluid, sat there, and frozen. Russian analyses reported extremely low cell counts and a small number of bacterial types, most of which the authors themselves identified as likely contaminants from the drilling operation. A separate genetic study of the accreted ice, the layer of lake water that freezes onto the underside of the ice sheet naturally, produced a long list of sequences including some from complex organisms, and was met with heavy criticism on contamination grounds. The current position among the researchers who work on this is roughly, the accreted ice does not provide clean evidence of an ecosystem. The borehole sample is compromised, and the question of what lives in Lake Vostok, if anything lives in it at all, is open. which is a remarkable place to be. The largest lake in Antarctica, one of the largest lakes on Earth by volume, and the honest state of knowledge about its biology is that we have not made a measurement anyone fully trusts. Compare that to Lake Whillans, entered the year after Vostok by an American team that had designed the access system from scratch specifically to avoid this outcome. Hot water drill, water filtered to a fine cutoff, ultraviolet sterilization of everything going down the hole, an independent contamination monitoring program. The samples they brought up showed roughly 130,000 cells per milliliter, thousands of distinct types, a full working ecosystem running on chemical energy from rock and sediment with no light and no oxygen. That result is trusted, and it changed how biologists think about the subsurface. Vostok is the older, larger, more isolated, more interesting lake, and it's the one where the answer is unusable. The unresolved boundary here is precise and slightly painful. It's not that Lake Vostok is unreachable. A hole has been put into it. It's that the first entry was made with the wrong equipment, for historical reasons that made sense at the time, and there's no established plan and no funded program to make a clean entry. Any future attempt has to deal with an existing contaminated borehole, an international treaty framework that has become considerably stricter, and the geopolitical reality that the site belongs to one nation's program. The measurement that would settle it is a fresh, clean access hole at a different point on the lake, using the Whillans-style protocol, and nobody has announced one. The second thing nobody has seen sits under the floating ice shelves, and the story of how it was found is a good demonstration of how thin our view of that world is. In 2021, a British Antarctic survey team was working on the Filchner-Ronne ice shelf. Their objective was mud. They wanted a sediment core from the seafloor beneath the shelf to reconstruct how the ice had behaved in the past. And to get it, they melted a borehole down through about 3,000 feet of ice and lowered a core through it, with a camera attached to watch the seabed as the core came down. The core hit rock, a boulder, sitting where the mud was supposed to be. The camera swung past it, and the footage came back with something the team was not looking for and had no reason to expect. The boulder was covered in animals, stationary ones, sponges or something very like sponges, and stalked filter feeders, 16 of one and about 22 of the other, anchored to the rock and doing what filter feeders do, sitting still with their mouths open, waiting for food to drift past. The location, and this is the whole point, was about 160 miles from the open ocean, under a permanent roof of ice, in water a couple of degrees below the freezing point of fresh water, in absolute darkness. Filter feeders that don't move have to eat what the current brings them. The current under an ice shelf brings whatever is suspended in it, and everything suspended in seawater ultimately traces back to photosynthesis, which requires sunlight, which does not exist under 3,000 feet of ice. Working from the known circulation, the team estimated that the nearest region where photosynthesis happens might be as much as 900 miles upstream of that boulder. 900 miles is a long way for a food particle to travel and still be worth eating. There are candidate explanations. The community might be sustained by an unusually efficient recycling of scarce organic matter. The circulation model might be wrong, and there might be a shorter route from productive water. There might be chemosynthesis involved, organisms building food from chemical reactions rather than from sunlight, which happens at deep sea vents and in subglacial lakes. Or the animals might grow so slowly and metabolize so slowly that the trickle is enough, and what looks like a thriving community is actually a very patient one operating on a time scale of decades. Nobody knows. And here's why nobody knows. The observation is a few minutes of video taken by accident, through a hole about 8 inches across, in an ice shelf the size of Spain. The team could not collect a specimen. They could not identify the species. They could not tell how old the animals were, or how fast they grew. The camera went past and then it was gone, and the hole refroze. That's the whole data set. It fits into a pattern that has been building for a decade. In 2015, an American drilling project punched through about 2,400 feet of the Ross Ice Shelf at the grounding zone of the Willans Ice Stream, roughly 530 miles from the open ocean, and sent a camera down. There were fish. Translucent pink fish about 8 inches long and crustaceans swimming around in 28-degree water under half a mile of ice, further south than fish had ever been recorded. The drillers had been expecting sterile mud. Every time we make a hole in an Antarctic ice shelf and point a camera through it, we find more life than the models predicted. And we have made, in total, a few dozen such holes, and the shelves cover an area larger than Texas and Alaska put together. And the same shortage of eyes applies out in the open water, past the ice edge, which is worth a detour because it makes the point without any ice shelf involved at all. The Southern Ocean holds an animal that has been known to science for a century and had never been seen alive. The colossal squid was described in 1925, from 2 arms recovered from the stomach of a sperm whale. Everything learned about it since came from the same source, or from specimens hauled up dead in fishing gear. Beaks and whale stomachs, a handful of bodies brought to the surface by longliners, one large individual, landed in the Ross Sea. Adults are estimated to reach around 23 feet and to be the heaviest invertebrate on the planet. The eyes are the largest known in the animal kingdom, roughly the size of a dinner plate, which is a design choice that only makes sense in permanent darkness with something very large hunting you. Nobody had ever watched one swim. In March of 2025, Delane Amphory and Barry Tweens, a remotely operated vehicle working near the South Sandwich Islands, on an expedition run jointly by an ocean census program, a research institute, and several universities, put a camera on one at about 2,000 feet down. It was a juvenile, roughly a foot long, almost completely transparent, drifting with its arms trailing. 100 years after the species was named, that was the first confirmed footage of a living colossal squid in its own habitat, a juvenile, a foot long. The adult, the 23-foot animal that leaves beaks the size of a fist in the stomachs of sperm whales, remains unfilmed. That is not a gap in the taxonomy. We know the animal exists, and we know roughly what it looks like. It's a gap in observation, and it exists because the deep Southern Ocean is enormous. The vehicles that can work there are few, and their field of view is a cone of light a few yards across in a water column that runs to more than 2 miles deep across an ocean that circles the planet. The chance of a camera and a large squid being in the same few cubic yards at the same moment is close to nothing, and it took a century for it to happen once with the small one. Working out how much of that roofed sea is inhabited by remote sensing is impossible. You cannot detect a sponge with a radar altimeter. There's no proxy. The only way to know is to go and look, one small hole at a time. And each hole is a season of logistics for a few minutes of video from a spot the size of a parking space. So the exact boundary, we have 4 or 5 direct observations of the seafloor community under Antarctic ice shelves. They have all been surprises. None of them has produced a specimen that could be formally described, and the mechanism feeding them is unknown. What would move it is a tethered vehicle that can range far from the borehole and collect, or better, an autonomous vehicle that can survey the cavity floor for miles and bring samples back to a different hole than the one it entered through. That's an engineering problem people are actively working on. Nobody has solved the sampling half of it yet. The third thing nobody has seen is the most photographed mystery on the continent, which is a strange thing to say about something invisible. In the McMurdo Dry Valleys, in a place called Taylor Valley, the snout of the Taylor Glacier ends in a wall of ice above a frozen lake. and down the face of that wall runs a stain the color of dried blood. It's called Blood Falls, and it has been photographed by every expedition that has gone near it since Griffith Taylor's party found it in 1911. Taylor's team thought the red came from algae. That was wrong. And for most of a century afterward, the standard explanation was iron oxidizing on contact with air, which is right in outline and turned out to be incomplete in a way that only got sorted out recently. Let me separate what's settled from what isn't, because this one gets described as unexplained when a large part of it is very well explained indeed. Settled. The liquid coming out is brine. Salt water 2 to 3 times saltier than the ocean. Cold enough that it stays liquid well below the freezing point of fresh water and loaded with dissolved iron. It emerges from under the glacier, hits the air, and the iron oxidizes. Also settled, as of a study published in 2023, exactly what the red material is, which had never actually been nailed down. Researchers took samples from the falls, ran them through a battery of techniques, and found that the red comes from amorphous nanospheres, where a century of assumption had put crystalline iron oxide minerals. Tiny, roughly spherical particles, too small and too disordered to register as a mineral on the standard tests, rich in iron but also carrying chlorine, silicon, calcium, and magnesium. They form when the dissolved iron in the brine meets oxygen, which explains, incidentally, why decades of mineralogical analysis kept coming back inconclusive. The instruments were looking for crystals, and there weren't any. Also settled. The biology, at least in outline. The brine carries a microbial community that runs without light and without oxygen, cycling iron and sulfur to extract energy. That was an important finding when it came out, because it demonstrated a viable subglacial metabolism and became one of the standard reference points for what life might do under the ice, of Europa or Enceladus. Now the part that is not settled, and it's the biggest part. Where is the brine coming from? Not in a vague sense, in the sense of there's a reservoir, and nobody has seen it, and nobody has sampled it, and the estimates of its size differ. The tracing has been done with electromagnetics rather than with a drill. In 2015, a team flew an airborne transient electromagnetic sensor slung under a helicopter over Taylor Valley. Salty water is strongly conductive, so a brine body under the ice lights up in that kind of survey. What they saw was not a puddle. They saw briny groundwater extending under a large part of the valley, connecting the glacier to the lakes and possibly to the ocean, which nobody had suspected. Follow-up work in 2017 used radio echo sounding to trace the pathways the brine takes through the glacier itself, showing that it moves through the cold ice in a network of channels, and that different pathways deliver it to different outlets. From all of that, the picture is a subglacial brine reservoir some miles upstream of the falls, under something like 1,300 feet of ice, feeding a plumbing system that occasionally opens at the glacier snout. Some miles. Something like. That's the resolution we have. Nobody knows the reservoir's volume, its depth, its temperature, its full chemistry, or how it's replenished, because the only instruments that have looked at it were flying overhead, sensing electrical conductivity from a distance. The leading interpretation of the brine's origin is that it's ancient seawater, trapped when a marine incursion flooded the valleys a few million years ago and then concentrated by freezing, since when water freezes it excludes salt, and the remaining liquid gets saltier. That's consistent with the chemistry. It's also, at this point, an interpretation rather than a demonstration, because a demonstration would require a sample from the reservoir and there has not been one. So put Blood Falls in the right column. The color, explained recently and in detail. The chemistry at the outlet, explained. The biology at the outlet, substantially explained. The source, located to within a few miles, never seen, never sampled, volume unknown, age inferred, And the measurement that would move it is a hot water borehole into the reservoir, in a valley that carries some of the strictest environmental protection on the continent, precisely because it's a pristine analog for other worlds, which makes drilling into it a decision with a high bar. That tension is real, and it's not going away. Those are the three that cannot be seen. Now a harder category, because in the next three we know exactly where to go. We know exactly what to measure. And the machine that would do it either doesn't exist or exists in a quantity of one. Start with the place that shows up in more headlines than any other feature in Antarctica. Thwaites Glacier drains a chunk of West Antarctica roughly the size of Florida. It's not the biggest glacier in Antarctica, but it occupies a position that makes it disproportionately important. Its bed slopes downward inland, so the further the grounding line retreats, the deeper the water gets, and the thicker the ice at the front becomes, which is a configuration that can feed on itself. And Thwaites sits like a cork in the flank of the West Antarctic ice sheet. Its own ice holds enough water to raise global sea level by more than 0.5 meter, which is close to 2 feet, and its removal would expose neighboring basins holding several times that. That's why it gets the attention. A great deal of that attention has been unhelpful, because the nickname it acquired implies a certainty about timing that nobody in the field claims. What's actually known is more specific and more interesting. The floating front of Thwaites is being melted from below by warm water, not warm in any human sense. Circumpolar deep water, the mass of relatively warm salty water that circulates around Antarctica at depth, runs a few degrees above the freezing point of seawater, and against ice, a few degrees is enormous. It reaches the front of Thwaites through troughs cut in the continental shelf, gets under the floating ice, and melts it. The critical zone is the grounding line, the boundary where the glacier stops sitting on bedrock and starts to float. That's where retreat is measured. That's where the geometry of the bed decides what happens next. Everything anyone wants to know about Thwaites converges on a band of ice a few miles wide, under 2,000 feet of ice, at the bottom of the world. In January of 2020, a hole was put through it. The operation gives you a feel for the scale of the difficulty. A hot water drill, flown in piece by piece and assembled on the ice, melting downward through roughly 2,000 feet of glacier to open a shaft about 16 inches in diameter. Through that shaft went a robot called IceFin, a tube-shaped autonomous underwater vehicle built to fit through a borehole and swim horizontally under the ice. It made 5 missions between the 9th and 11th of January. 5 missions. That's the entire history of direct human observation at the grounding zone of the glacier that dominates the sea level conversation. And the results were not what the models said. The water at the grounding zone was warm, well above the in situ freezing point, exactly as expected. But the melting was suppressed. A thin, cold, fresh layer of meltwater was sitting against the underside of the ice, and it was stable, and it was insulating the ice from the warm water a few feet below. The currents were too weak to mix it away. Over the flat underside of the ice, melt rates were lower than the models had assumed. Then IceFin looked at the crevasses, where the ice base had structure. Along vertical steps and inside the walls of crevasses, the melt was fast. The stratification that protected the flat ceiling broke down against a vertical surface. Water could circulate. The result is a picture where the ice isn't melting evenly from below at all. It's being cut along the fractures, which widen, which creates more vertical surface, which cuts faster. The glacier is being taken apart along its weaknesses rather than shaved off its bottom. That reframes the problem, and it does so in a way that makes prediction harder because the models were built around a flat ceiling and a uniform melt rate. And the real system is dominated by geometry at the scale of individual crevasses, which no ice sheet model resolves. So here's the unreachable part. To know how Thwaites will behave, you need observations along the grounding line over time. The grounding line of Thwaites is something like 70 miles long. We have 5 vehicle missions at one point on it, over 3 days, 6 years ago. Why not more? Because everything about that campaign was at the limit. The site is a 2-hour flight from the nearest station, on a surface riven with crevasses that make landing an aircraft a survey problem in itself. The drill needs fuel, and the fuel arrives by air. The window is a few weeks. The vehicle has to work the first time. The international collaboration that made it happen was a multi-year, multi-nation effort involving dozens of researchers and 2 national programs, and it produced 3 days of data at one spot. The measurement that would move this is a fleet of long-endurance autonomous vehicles that can be deployed once and left to patrol the subshelf cavity for a year, surfacing at the ice front to report. The technology is close. Vehicles have made long under ice transits. What doesn't exist yet is one that can do it repeatedly, in a crevassed cavity, without a tether or a human within 1,000 miles. Until it does, the most consequential piece of ice on the planet is being modeled from a few days of measurements at one location, and every honest projection you read about Thwaites carries that on its shoulders. The second unreachable thing is not a place. It's a stretch of time, and the reason we cannot get at it is that the archive holding it is being destroyed from underneath by the very heat that keeps it in one piece. An ice core is a recording. Snow falls, traps air bubbles, gets buried, compresses into ice, and those bubbles hold actual samples of the atmosphere from the year the snow fell. Most deep climate records are proxies, reconstructed from tree rings or lake sediment or the chemistry of shells. This one is the gas itself. You can crack the ice open in a lab and measure the carbon dioxide in a bubble that was sealed while mammoths were walking around. The European ice coring effort at Dome C, drilled in the early 2000s, produced a continuous record going back about 800,000 years, 8 full glacial cycles, with the composition of the atmosphere measured directly through every one of them. That core is the backbone of a large fraction of what's known about how carbon dioxide and temperature have moved together over the deep past. And it stops at a wall, and just past the wall is the thing everyone wants. Somewhere between roughly 1.2 million and 800,000 years ago, the rhythm of the ice ages changed. Before that period, glacial cycles ran on a roughly 41,000-year beat. After it, they ran on a roughly 100,000-year beat, and they got deeper and more asymmetric. This is called the mid-Pleistocene transition, and it happened without any corresponding change in the orbital forcing that's supposed to set the pace. The Earth's wobble kept doing what it had been doing. The climate response to it reorganized. Something internal to the climate system changed. The leading candidates involve carbon dioxide, or the slow erosion of the sediment layer under the northern ice sheets, or both. To distinguish between them, you would want a direct measurement of atmospheric carbon dioxide across the transition, which means ice older than 800,000 years, continuous, with intact bubbles. Getting it is a physical problem, and the physics is against you. Ice sheets flow. Old ice at the bottom gets stretched, thinned, and sheared, and the layers that represent individual years compress from feet to inches to fractions of an inch until they cannot be separated. Worse, if the bed is warm, the oldest ice is melting away from below as fast as new ice arrives from above, which means the archive has a maximum age set by the geothermal heat flux. And the geothermal heat flux, as we saw, is a number known at fewer than 20 points on the entire continent. So the search for old ice is a search for a very specific and rare combination. Thick ice, so there's a lot of record, but a bed cold enough that the bottom hasn't melted, and ice that flows slowly enough that the layers are not sheared into unreadability, sitting on a bed flat enough that the layers stay in order. Those conditions do not coexist in many places. The site that emerged from years of radar surveys is Little Dome C, on the East Antarctic Plateau at about 10,500 feet of elevation, not far from the original Dome C core. The Beyond Epica project drilled there for 4 consecutive summers, in average temperatures around 35 below 0 Celsius, which is roughly 31 below 0 Fahrenheit, with a team of about 16 people living at a camp in the middle of the plateau. In January of 2025, they reached bedrock. The hole went down about 2,800 meters, which is a little over 9,000 feet, or roughly 1 3/4 miles. And the record came up. Continuous ice covering at least 1.2 million years, with the interval from 800,000 to 1.2 million years sitting in a band of core somewhere around 2,400 to 2,500 meters deep. The mid-Pleistocene transition, in ice, in a freezer, in Italy, that's a magnificent result, and it deserves to be celebrated. It's also the point where the unreachable part starts. Look at those depths. The interval that took the atmosphere through 400,000 years of the most interesting reorganization in recent geological history is compressed into something like 70 meters of core. A little over 200 feet of ice to hold 400,000 years. In the upper part of an ice core, a single year might occupy an inch or more. Down there, 1,000 years occupies less than an inch. The analytical challenge of extracting a clean signal from layers that thin in ice that has been under enormous pressure for 1,000,000 years is at the edge of what the instruments can do, and some of the signals of interest diffuse within the ice over that kind of timescale. And the very bottom, the ice sitting directly on rock, is a different problem again. Basal ice is typically disturbed. It's been dragged, folded, refrozen, and mixed with material from the bed. Whether the oldest portion of the Beyond Epica core is stratigraphically continuous all the way down, or whether the sequence gets scrambled somewhere near the bottom, is exactly the kind of question that takes years of analysis to answer, and may not resolve cleanly. So what's still out of reach is not the 1.2 million year mark. That's been achieved. It's everything before it. There are radar indications of ice possibly older still in parts of East Antarctica, and there's real interest in reaching 1.5 million years or further to capture the beginning of the transition rather than its end. Finding such a site requires surveys in the interior, which puts us back in the blank corridors of the bed map. Drilling it requires another multi-year international campaign, and there's a hard ceiling somewhere, set by geothermal heat, beyond which no ice on this planet has survived, and nobody knows exactly where that ceiling is because it depends on the heat flux field we cannot measure. The third thing beyond reach is under West Antarctica, and it's the one where the gap between what we've detected and what we can assess is widest. In 2017, a research group at the University of Edinburgh went through the aerial and satellite datasets covering West Antarctica, looking for a specific shape, a cone. Volcanoes have a characteristic geometry, and the bed topography maps had gotten good enough that you could go hunting for cones in the rock beneath the ice the way you'd hunt for them on a map of Mars. They found 91 that nobody had cataloged. Added to the 47 already known, that put the total at 138 volcanic structures in the West Antarctic Rift system, which by that count makes it one of the largest concentrations of volcanoes anywhere on Earth, denser in places than East Africa. The identification is convincing. The West Antarctic Rift system is a real tectonic feature, a zone where the crust is being pulled apart, and rifts produce volcanoes. There are known active volcanoes in the region above the ice, most famously Mount Erebus over on Ross Island, which has held an open lava lake continuously since at least 1972. Erebus is worth a sentence of its own, incidentally, because its lava lake is made of phonolite, a viscous, gas-rich magma that has no business maintaining an open, convecting lake at all. Open lava lakes are supposed to be a basalt phenomenon, and why Erebus manages it is still being worked out. Here's the question about the 138 that nobody can answer. How many of them are active? Not in the sense of erupting today, in the sense of capable of erupting, with magma in the system, on a timescale that matters. That distinction is the whole game because a volcano under an ice sheet does something a volcano in the open air does not. It delivers heat directly into the base of the ice. An eruption under a glacier melts an enormous volume of water very quickly, and that water goes into the subglacial drainage system, and the drainage system controls how fast the ice above slides. There's radar evidence of at least one subglacial eruption in West Antarctica within the last couple of thousand years, from a layer of ash buried in the ice. And there are regions where the ice appears to be losing mass in ways that are hard to explain from ocean melting alone, where extra basal heat would help the numbers work. The evidence that at least one of them has gone off recently is a layer in the ice, and finding it was a nice piece of detective work. Flying radar over the Hudson Mountains in West Antarctica, a British team picked up a strong, extensive reflector well above the bed of the ice sheet, where reflectors are not supposed to be, a horizon inside the ice itself, spread over hundreds of square miles, at a depth that corresponded to a particular date in the layer sequence. The interpretation was an ash and rock debris layer from a subglacial eruption that broke through the ice surface and dusted the region, roughly 2,300 years ago, which in geological terms is the day before yesterday. The ice above it has kept the layer intact ever since. That eruption happened in a region that now hosts some of the fastest thinning ice in Antarctica. Whether there's any connection is not established, and it would be irresponsible to claim one. And the honest position is that we have a demonstrated capability for eruption in that sector, no ability to monitor it, and glaciers behaving in ways that basal heat would help explain. Assessing volcanic activity normally means seismometers, gas measurements, ground deformation surveys, and rock samples for dating. In West Antarctica, you cannot sample the rock because it's under a mile of ice. You cannot measure the gas because it dissolves into the meltwater and never reaches the atmosphere. Ground deformation is measured on a surface that's moving hundreds of feet a year on its own, and seismometers left on an ice sheet record the ice constantly. Ice cracks. Ice streams stick and slip and generate signals that look like earthquakes. Separating a volcanic tremor from the background noise of a moving glacier is a hard signal processing problem, and the network density needed to even attempt it is far beyond what's out there. So the boundary is unusually clean on this one. We have a catalog of 138 volcanic edifices, an excellent tectonic reason to believe some are live, ash layers proving at least one has erupted recently in geological terms, and no capability whatsoever to tell you which ones. The measurement that would move it is a dense, long-duration seismic and magnetotelluric network over the rift, capable of imaging magma bodies in the crust. That's a decade-long, continent-scale instrumentation program. Nothing on that scale is funded. Those are the three we cannot reach. What comes next is a different kind of frustration entirely, because in the following four, the data is not the problem. The data is fine. It's the meaning of the data that people cannot agree on. And in two of these cases, the disagreement is between researchers who are each, on their own terms, being completely reasonable. Begin with the one that has been kidnapped by the internet more thoroughly than anything else on the continent. In 2006, a team led by researchers at Ohio State reported something odd in data from a pair of satellites called GRACE. The GRACE mission worked by flying two spacecraft in formation, about 130 miles apart, and measuring the distance between them with extraordinary precision. When the leading satellite passes over a region where the Earth's mass is concentrated, gravity tugs it forward slightly, and the gap between the two spacecraft changes by a fraction of the width of a human hair. From those changes, you can map the Earth's gravity field, and from the gravity field you can infer where mass is piled up underground. Over north-central Wilkes Land in East Antarctica, around 70 degrees south and 120 degrees east, GRACE showed a positive gravity anomaly, a mass concentration. And underneath the ice, The bed topography showed a large circular basin, roughly 300 miles across. A dense mass sitting inside a big circular depression is a combination with a well-known cause elsewhere in the solar system. Large impacts punch a crater and the mantle underneath rebounds upward, leaving denser material closer to the surface. You see that pattern on the Moon, where those features are literally called mascons. The Ohio State team argued the Wilkes land structure fit. If it's an impact basin, it's nearly 3 times the diameter of Chicxulub, the crater associated with the end of the dinosaurs. That comparison, plus a rough coincidence in timing with the Permian extinction, produced headlines that have been recycled continuously for 20 years. Then it got attached to everything else. The circular structure under the ice became, in various corners of the internet, a buried city, a crashed craft, an installation, an entrance. Let me be blunt, because it obscures a real scientific dispute. There's no evidence of anything artificial in Wilkes Land, and no serious researcher has ever suggested there is. What exists is a gravity signal and a basin. The real dispute is between geophysicists, and it's substantive. The impact interpretation has never been accepted by most of the field, for reasons that come down to what gravity data can and cannot tell you. A positive gravity anomaly in a basin is consistent with an impact. It's equally consistent with a mantle plume, with an old volcanic province, with a dense block of crust inherited from a much earlier assembly of the continent, or with the structure of a rift. East Antarctica is a collage of ancient crustal blocks that were welded together in various collisions going back well over 1 billion years. And the boundaries between those blocks routinely produce exactly this kind of density contrast. There's a lot of aeromagnetic data over the region now, and the picture that has emerged looks more like inherited tectonic architecture than like a scar. The basin's circularity, which is what makes it look like a crater in a picture, is also less compelling than it appears. Subglacial basins in East Antarctica are frequently roundish because they've been excavated by ice flowing outward from a dome, and radially flowing ice carves radially symmetric hollows. Here's what makes this undecidable at present rather than merely contested. Confirming an impact structure requires physical evidence in the rock. Shocked quartz, with the specific crystal deformation that only extreme pressure produces. Impact melt. Shatter cones. A layer of ejecta somewhere in the global record with the right chemistry and the right age. None of that can be produced from a gravity map, and all of it requires rock samples. The rock in question is under more than a mile of ice, in one of the least accessible parts of East Antarctica, hundreds of miles from any station, in a region where, as established, the bed itself is mapped from widely spaced flight lines. Drilling to bedrock through a mile of ice at a remote inland site is a several-season project on its own, and you'd need to hit the right spot. So the anomaly sits there. Real, measured, mapped in increasing detail, interpreted 2 incompatible ways by qualified people, and unresolvable without a rock sample nobody is currently able to collect. That is a legitimate open question, and it does not need a spaceship in it to be worth your attention. The second dispute is about something that happens in plain sight, is measured continuously by satellites, and made every model in the field look wrong twice in a decade. Sea ice around Antarctica is a separate system from the ice sheet. Frozen ocean surface, mostly a few feet thick, that forms in autumn, expands through winter to cover an area larger than the continent itself, and then melts back almost entirely each summer. Satellites have measured its extent continuously since 1979, which gives one of the cleanest, longest, least ambiguous environmental records that exists. Here's the record. For about 35 years, Antarctic sea ice extent trended slightly upward, not dramatically, but persistently, and in the wrong direction for what everyone expected. The Arctic was losing ice fast and visibly, and the Antarctic was gaining a little. and it reached a satellite era maximum in 2014. That was awkward, and it got used politically. And the honest scientific position at the time was that nobody had a settled explanation. There were candidate mechanisms: strengthening westerly winds pushing ice outward, meltwater from the ice sheet freshening the surface layer and making it easier to freeze, changes in ocean stratification trapping heat below. Each could produce some of the observed growth. The models, run collectively, mostly predicted a decline. They got the sign wrong for 3 decades. Then it reversed, hard. Beginning around 2016, Antarctic sea ice fell off a cliff. Summer minimums hit record lows repeatedly. And in 2023, the winter maximum, the annual peak, came in at about 16.96 million square kilometers, which is roughly 6.5 million square miles. That was more than 1 million square kilometers below the previous record low maximum from 1986. Better than 380,000 square miles of missing winter ice, compared with the worst previous year in the record. To put that in the right frame, an area of ocean larger than Texas and Colorado put together, which should have been frozen at the peak of winter, was open water. The statistical language used about that event is unusual. Several analyses described it as a multiple sigma departure, an event that, under the previously observed variability, should occur on a timescale of millennia. And it did not bounce back. The years since have stayed low. So the state of the science is that a major component of the Earth system trended one way for 35 years in a manner no model reproduced, then flipped to a state no model predicted. And the leading interpretation is that the ocean underneath has changed in a way that makes the old growth mechanisms unable to operate. Warmer water at depth, reaching closer to the surface, providing enough heat to slow freezing regardless of what the winds do. Some researchers argue the system has passed into a new regime and will not return to the old one. Others argue it's a large excursion within variability that hasn't run its course. That disagreement is not resolvable from the surface record alone, and here's why it connects to everything else. To tell the difference between a temporary excursion and a regime change. Cherise, you need to know what the water column under the ice is doing through the winter, year after year, which is the measurement, established earlier, that we do not have. There's a consequence attached to this that gets less attention than the sea level arithmetic, and it's the one I find hardest to be dispassionate about. Emperor penguins breed on sea ice, not on land, not on the ice sheet. On the flat, fast ice that forms against the coast and stays anchored there through winter. The timing is unforgiving. They arrive in autumn, lay in winter, and the chicks need until roughly December or January to grow waterproof feathers. If the ice under the colony breaks up before the chicks have fledged, the chicks go into the water without waterproofing, and they do not survive it. In the spring of 2022, the fast ice in the Bellingshausen Sea sector broke up early and comprehensively. Satellite imagery of 5 emperor colonies in that region showed that 4 of them lost their ice before the chicks could fledge. The breeding season for those colonies produced essentially nothing. That's not an extinction event, and it should not be reported as one. Emperors have around 66 known colonies, several of which were only located in the last few years, by spotting the stain their droppings leave on the snow in satellite images, and colonies do relocate when conditions change. Several have already shifted by 25 miles or so in search of stable ice. The species has options. What the 2022 failures demonstrate is that the sea ice question stopped being abstract. A statistical anomaly in a satellite time series turned into 4 colonies of birds standing on ice that went out from under them in one season in one sector, and nobody predicted it because nobody can currently predict the ice. The satellite record of Antarctic sea ice is nearly perfect, and it's only 2-dimensional. It tells you the area with astonishing fidelity and tells you almost nothing about thickness, which is what actually matters for volume, and nothing at all about the water below. Estimating Antarctic sea ice thickness from orbit is far harder than in the Arctic, because Antarctic sea ice carries deep snow that depresses the flow and confuses the altimeter. So the exact boundary. We can measure the extent to within a few thousand square miles, and we cannot tell you the volume with confidence. We do not have an accepted explanation for the 3-decade growth. We do not have an accepted explanation for the collapse, and the observations that would distinguish between the competing accounts are under the ice in winter, where the ships cannot go. The third dispute is the most consequential argument in Antarctic science, and it turns on whether a specific physical process happens at all. Ice has a limit to how tall a vertical cliff it can support. Push past it, and the cliff fails under its own weight. You can watch this at any calving glacier front in Greenland or Alaska. The face rises out of the water, cracks propagate, and a section collapses. In practice, ice cliffs standing in water seem to top out somewhere around 300 feet above the waterline before they start failing routinely. Now consider what happens to a marine glacier whose floating ice shelf is removed. The shelf was holding the ice behind it back. Take it away, and the glacier's front becomes an exposed cliff, standing in deep water, with a height set by how thick the ice was. On the deep beds of West Antarctica, that cliff could be far taller than the stable limit. The hypothesis, published in 2016 by Robert DeCanto and David Pollard, is that such a cliff would collapse, and then the ice behind it, now exposed, would form a new cliff, which would also be too tall, and would also collapse. And so on, inland, along a bed that deepens as you go. So each new cliff is taller than the last, a self-sustaining retreat that runs until it reaches shallower ground or higher terrain. They called it marine ice cliff instability. When they put that mechanism into an ice sheet model and ran it forward under a high-emission scenario, Antarctica contributed something in the neighborhood of a meter of sea level rise by the end of this century, around 3 feet from Antarctica alone, on top of everything else. That's several times what the models without the mechanism produced, and it was the origin of a great many alarming headlines in the years that followed. The counter-argument arrived properly in 2019, led by Tamsin Edwards, and it's a model of how this kind of dispute should be conducted. Rather than asserting the mechanism doesn't happen, that work asked a sharper question. Is the mechanism required by the evidence? The test used the past. There have been periods when the Earth was warmer than today, and Antarctica lost a lot of ice. The mid-Pliocene, about 3 million years ago, and the last interglacial, about 125,000 years ago. There's also the satellite era record from 1992 to 2017. If ice cliff instability is a real and important process, models including it should reproduce those past ice losses better than models without it. They found that it wasn't necessary. Models without cliff instability reproduced all 3 periods adequately. And once you properly propagate the uncertainty in the model parameters, the projections come down a great deal. Their most likely value for Antarctica's contribution under very high emissions was around 45 centimeters, roughly 18 inches, with the upper end of the range well below the earlier figures. Then a further round, published in 2024, took a different approach again. 3 separate ice sheet models were given a hypothetical scenario in which all the floating ice in the Amundsen Sea sector vanished instantly, which is the worst-case starting condition for cliff collapse. A physically motivated treatment of the cliff mechanics was built into each. All 3 models produced the same answer. Thwaites would not run away this century. The cliffs that formed would be buttressed by the debris of their own collapse, the melange of broken ice packed in front of the glacier, which acts like a jam in a river and holds the face up, at which point you might reasonably conclude the matter is settled. And I don't think it is, and neither do most of the people involved. Here's why. Marine ice cliff instability has never been observed at the scale that matters. The tallest ice cliffs on Earth today are a fraction of the height the hypothesis concerns. Every model of how a 2,000-foot ice cliff fails is an extrapolation from cliffs a few hundred feet tall, using material properties of ice, measured in laboratories on samples the size of a coffee can, applied to a structure the size of a mountain range. The melange buttressing result depends on how the broken ice packs and how long it stays in conditions nobody has watched. The strength of ice at those scales depends on pre-existing fractures, which depend on the flow history, which the models simplify heavily. So the dispute is not about who read the data correctly. Everyone agrees on the data. The dispute is about how a material behaves in a configuration that does not currently exist anywhere on this planet. And the only way to observe it directly is to wait until it happens, which is the one experiment nobody wants to run. What would move it? Better constraints on ice fracture at large scale, from field observations of the tallest existing cliffs in Greenland, and from the geological record, looking for evidence of past retreat rates fast enough to require the mechanism. Both are being pursued. Meanwhile, the upper bound on how much sea level rise Antarctica can deliver this century remains an argument about a process that may or may not exist. The fourth dispute is older, quieter, and it concerns an entire mountain range that has an alpine landscape carved into it and is buried under the middle of the East Antarctic Plateau. The Gomburtsev subglacial mountains were discovered by a Soviet traverse in 1958, essentially by accident, using seismic sounding across a part of the plateau where the surface is flat, featureless, and gives no hint of anything underneath. What they found was a mountain range, peaks reaching close to 9,000 feet above sea level, buried under ice that runs from a few thousand feet thick over the summits to well over a mile in the valleys. That alone was surprising. What made it a genuine problem is the shape. The Antarctic Gomburtsev Province Survey, flown during the International Polar Year in 2008 and 2009, put radar, gravity, and magnetic instruments over the range and produced a detailed picture. And the picture shows a classic alpine landscape: sharp peaks, deep, steep-sided valleys, with the characteristic profile of glacial erosion. A dendritic network of valleys that started as river valleys and were later deepened by ice. That's the landscape of a young mountain range. The Alps look like that. The Rockies look like that. Sharp topography erodes. And on a continent that has been sitting under an ice sheet for over 30 million years, you'd expect either heavy modification or preservation of something much more subdued. But the geology says the crustal root under the Gomburtsevs is ancient. The survey found a thick root beneath the range and a rift system, roughly 1,500 miles long, wrapped around it. The interpretation published in 2011 is that the root formed during the assembly of interior East Antarctica, possibly around 1 billion years ago, and then sat there, dormant, through most of Earth's subsequent history. Later rifting, in the Permian around 250 million years ago and again in the Cretaceous around 100 million years ago, reactivated it. Rift flank uplift, buoyancy from the old root, and isostatic response to erosion lifted the range, and rivers and then glaciers carved it. So the answer offered is that the mountains are old in their foundations and young in their topography, lifted by a mechanism that doesn't require a collision, and preserved because the ice sheet froze onto them early and stopped eroding them. That's a coherent story, and it's the most widely cited one. It's not the only one on the table. Other researchers have argued for erosion-driven uplift as the dominant control, where the carving of the valleys itself unloads the crust enough to push the peaks up. The relative importance of rifting, of the ancient root, and of erosional unloading is not agreed, and there's no direct evidence for any of it, in the sense that matters most. Nobody has a rock. Not a single sample of the Gomburtsev Mountains exists. Every statement about their age and composition is inferred from the magnetic and gravity signature of rock nobody has touched, calibrated against rock exposed elsewhere in East Antarctica. There's one indirect source: sediment eroded from the range and carried to the coast, which has been recovered in offshore drill cores and dated, and which supports an old crustal history. That's a real constraint, and it's the best available. It's also a sample of the debris rather than the mountain. The same argument, in a different form, runs along the Transantarctic Mountains, the range that splits the continent for about 2,200 miles and reaches around 15,000 feet. Those you can walk on, and geologists have, extensively. And their uplift is disputed too because they show none of the folding or thrust faulting that continental collisions produce. Several mechanisms have been proposed: rift flank uplift, thermal buoyancy, flexural response to unloading, and after decades of work, there's no consensus about which dominates. A mountain range you can climb, mapped in detail, and the reason it's tall is unresolved. While we're in these mountains, this is the right place to deal with the pyramid. Every couple of years, an image circulates of a peak in the Ellsworth Mountains that is almost perfectly pyramidal, with 4 sharp faces meeting at a point. And it gets presented as a structure. It's a nunatak, a mountain peak protruding through the ice, and its shape has a textbook explanation. Glaciers eroding a peak from several sides simultaneously cut back the faces until what's left is a sharp horn. The Matterhorn is the same landform. Nature produces 4-sided pyramids readily when 4 glaciers converge on one summit, and the Ellsworths have exactly the glacial configuration to do it. The interesting thing about that peak has nothing to do with its silhouette. It's that the Ellsworth Mountains contain rocks that don't match the block of crust they're sitting next to, which is part of the evidence that West Antarctica is a collection of fragments that arrived from different places and got assembled. That's a better mystery than a pyramid, and it's a real one. 4 disputes, and a pattern in all 4. The argument is about what you're allowed to conclude from measurements taken at a distance. And in 3 of the 4, the thing that would end the argument is a physical sample of rock or ice from a place that's currently out of reach. The last 3 are different again, and they're the purest form of the thing. In these, we have the observations, we have plenty of them, nobody disputes them, and the explanation is simply not there. In the Wright Valley, one of the McMurdo Dry Valleys, there's a puddle. That's the honest description. Don Juan Pond is a few hundred yards long, a few inches deep in most places, and it looks like meltwater pooled on gravel. A person could walk across it without getting their knees wet. In photographs, it's so unimpressive that it takes a moment to understand why anyone flew there. It's the saltiest body of water on Earth, by a wide margin, and it does not freeze. The Dead Sea runs around 34% salinity. Don Juan Pond runs above 40%, and the salt doing the work is calcium chloride, which is the compound people spread on roads in the northeast to melt ice, and which suppresses the freezing point far more aggressively than table salt does. The pond stays liquid down to something around 58 degrees below 0 Fahrenheit. Air temperatures in the Wright Valley go below that occasionally, and observers have recorded the pond liquid at temperatures that would freeze the ocean solid several times over. The water has a viscous, syrupy feel. It supports essentially no life, which in itself is notable, because almost nothing on this planet is too extreme for something. Don Juan Pond appears to be close to it. The water activity, the measure of how available water is to an organism regardless of how much of it is present, is low enough that known life cannot use it. It has also been, for roughly 60 years, the single most cited terrestrial analog for liquid water on Mars, because calcium chloride brines are exactly what would stay liquid under Martian conditions, and because features on Martian slopes have been interpreted as brine flows. If you want to understand what a Martian seep might be, you study this puddle. And the question of where the salt comes from has been argued continuously since the 1960s without resolution. There are two accounts, both defended in the peer-reviewed literature within the last decade, and they imply completely different things about the valley. The first is deep groundwater. In this account, there's a groundwater system in the Wright Valley, running below the permafrost, carrying calcium chloride brine, dissolved out of the surrounding rock over a very long time. The brine wells up at the low point of the valley, which is where the pond sits, and evaporation concentrates it further. Boreholes drilled in the 1960s did find saline groundwater beneath the pond, which is a real observation supporting this. A 2017 geochemical study argued that the specific ionic ratios in the pond water can only be produced by a deep source, and estimated that the pond's water turns over roughly every 6 months, which requires substantial continuous recharge from below. The second account is deliquescence, and it's much stranger. Calcium chloride salts are hygroscopic to an extreme degree. Leave calcium chloride crystals in air with even modest humidity, and they pull water vapor out of the atmosphere and dissolve themselves in it. The threshold humidity for that can be as low as around 12%, depending on temperature and on the hydration state of the crystals. And the slopes above Don Juan Pond are covered in calcium chloride salt deposits. In this account, the pond is fed from above, not below. Salt on the valley walls absorbs moisture from the air, forms brine. That brine trickles down slope and combines with small amounts of snowmelt to fill the pond. Research led from Brown University, published in 2013, set up time-lapse cameras and weather instruments in the valley and documented exactly this: brine tracks appearing on the slopes during humid periods, water levels in the pond responding to those events and to summer melt. With no observed groundwater contribution during the monitoring period, both sides have field data, both have published, neither has conceded, and the reason it matters beyond the pond itself is Mars. If the brine is fed by deep groundwater, then the analog for Martian brine features requires a subsurface aquifer, which is a strong claim about Mars. If it's fed by deliquescence, then a Martian slopestreak needs only salt and a thin, occasionally humid atmosphere, and nothing underneath. The two mechanisms make different predictions about where to look for water on another planet, which is why a puddle in a dry valley in Antarctica keeps getting funded. The measurement that would settle it is not exotic. A properly instrumented borehole network in the Wright Valley, monitored across multiple seasons, tracking pressure and chemistry in the subsurface continuously rather than sampling it once. The obstacle is that the dry valleys are among the most strictly protected environments on the continent. The drilling footprint would be in the most sensitive part of them, and the science community has been reluctant to disturb the very thing that makes the site valuable. The dispute persists partly because resolving it would damage the specimen. The second unresolved item is the strangest thing in this whole survey, and it's about objects that fall out of the sky. Antarctica is the best place on Earth to collect meteorites, and the reason is a beautiful piece of natural machinery. Meteorites fall everywhere on the planet at roughly the same rate. In most places, they land in vegetation, ocean, farmland, or forest, and they weather, corrode, and disappear, and you'd never find them. In Antarctica, they land on snow and get buried. Then the ice sheet carries them, slowly, for tens of thousands of years, flowing outward from the interior toward the coast. When that flow runs into an obstruction, typically a buried mountain range, the ice is forced upward. At the surface, in certain areas, fierce dry winds scour away the ice as fast as it rises, a process called ablation. The ice evaporates. The rocks it was carrying do not. So the ice sheet works as a conveyor belt and a concentrator. It gathers meteorites over a vast area and a vast span of time and deposits them in specific blue ice fields, sitting on the surface, dark objects on a clean white background, visible from a snowmobile. Over 50 years of collecting, more than 45,000 meteorites have been recovered from Antarctica. It's the majority of the world's collection. Here's the anomaly. Meteorites come in broad classes. Most are stony. A small fraction are iron, essentially solid metal, fragments of the cores of shattered planetesimals. Worldwide, among meteorites observed to fall and then recovered, iron meteorites account for roughly 5.5 out of every 100. In the Antarctic collections, they account for under 1 in 100. A factor of 5 or more in a collection large enough that statistical fluctuation cannot explain it. Something in Antarctica is systematically removing iron meteorites from the population or preventing them from reaching the surface. The explanation proposed in 2016 by a team including Jeffrey Evatt at Manchester is elegant enough that it deserves to be true. Iron conducts heat far better than rock does. A dark iron meteorite sitting just below a translucent ice surface absorbs sunlight that penetrates the ice, and being metal, it distributes that heat efficiently to the ice immediately around it, melting it. The meteorite sinks into the meltwater, and the water refreezes above it. It burrows downward. Meanwhile, the ice around it is rising, carried up by the flow against the mountain barrier. If the burrowing rate roughly matches the rising rate, the meteorite never surfaces. It gets stuck permanently at a shallow depth, hovering, while stony meteorites with lower conductivity make it to the top and get collected. The team tested the mechanism in the laboratory with real meteorite samples embedded in ice and published the result. It works. Iron samples sink under illumination in a way stony samples do not, and the model made a prediction that is unusually crisp for this field. There should be a layer of iron meteorites sitting a few inches to a foot or so below the surface of the blue ice fields, in numbers that would make it one of the richest metal deposits per acre anywhere. That prediction is testable with a metal detector. So a British-led project, the Lost Meteorites of Antarctica, went and did it. Field campaigns towed purpose, built wide-array metal detectors behind snowmobiles across blue ice fields, in seasons across the late 2010s and into the 2020s, hunting for buried metal in a place with no natural background of metal to confuse the signal. They recovered meteorites, over 100 of them, from the surface, which is a good haul in itself. What they did not do is confirm the buried iron layer. The campaigns produced valuable data on how the detection works and on where the concentration mechanism operates. And the specific prediction of a shallow, dense population of hidden iron meteorites has not been demonstrated. So the situation now is that we have a robust, well-quantified observation that iron meteorites are missing from Antarctica, a physically sound mechanism that explains it and has been verified in the lab, and no field confirmation of the mechanism's main consequence. Either the layer is there and the search areas were wrong, or the sinking is real but the numbers work out differently in the field than in the lab, or the depletion has a different cause nobody has proposed. The measurement that would move it is more detector coverage across more blue ice fields, guided by better modeling of where the conveyor concentrates material. That work is ongoing and cheap by Antarctic standards. It's one of the few items in this whole survey that might be settled within a few years by people who are already out there looking. The last one is the largest single thing Antarctica does to the rest of the planet, and the part we cannot account for is where it happens. Go to the edge of the continent in winter in the right places. Along certain stretches of coast, the wind comes down off the ice sheet with a particular brutality. Cold air is dense, it pools on the high interior plateau, and gravity drains it downhill toward the coast, accelerating as it goes. These are katabatic winds, and along some coastlines they arrive at the sea at highway speeds and never stop. What that wind does to the water is the engine of the deep ocean. It pushes newly formed sea ice away from the coast continuously. Open water is exposed. Open water at those air temperatures freezes almost immediately. That new ice gets pushed away too, and more water is exposed and freezes. These are coastal polynyas, and they operate as ice factories, converting seawater to sea ice at an industrial rate all winter long. And here's the part that matters. When seawater freezes, the salt doesn't go into the ice. It gets rejected, expelled into the water below as an intensely salty, intensely cold brine. That brine is the densest water produced anywhere on the surface of this planet. It sinks, it slides down the continental slope, entrains other water on the way, and settles into the deepest basins of the world ocean. That's Antarctic bottom water. It fills the bottom of the Atlantic, the Pacific, and the Indian Oceans. Somewhere between a third and a half of the volume of the entire world ocean, by some accountings, has this origin. When it sinks, it takes dissolved oxygen with it, which is what keeps the deep sea habitable, and it takes carbon with it, which is a substantial part of why the ocean has absorbed as much of our emissions as it has. The water at the bottom of the Pacific, 3 miles down off California, was at the surface off Antarctica, breathing, 1,000 years ago. The measurements say it's slowing down and shrinking. Repeat hydrographic sections, ship transects that go to the same coordinates every decade and lower instruments to the seafloor, have documented the abyssal layer warming and contracting for 30 years. Work led from CSIRO in Australia and the University of Southampton, published in 2023, put the slowdown of the deep overturning at around 30% between the 1990s and the 2010s. Separate analyses of the Weddell Sea found the volume of the densest bottom water there down by roughly 30% since 1992, with the sharpest losses in the very densest classes, and linked it to a decline of better than 40% in the rate of sea ice formation on the southern shelf. The mechanism is understood in outline. Meltwater from the ice sheet freshens the surface water near the coast. Fresher water is more buoyant. Buoyant water resists sinking. And the brine rejection from the ice factories has to overcome a bigger deficit to make water dense enough to reach the bottom. Less bottom water is formed. The deep layer, no longer being replenished at the old rate, one warms and thins from below. Now the unresolved part, and it's more basic than you might expect from a process this well documented. We do not know how many places make this water. For most of the 20th century, the textbook answer was 3: the Weddell Sea, the Ross Sea, and the Adelie Land Coast. 3 source regions, feeding the bottom of the world. Then in 2013, an Australian and Japanese team working off the Cape Darnley Polynya in East Antarctica found a 4th, producing a significant share of the total, in a place that had been sampled far too rarely for anyone to have noticed. It had presumably been doing that continuously for as long as the others. A 4th source of the water that fills the bottom of every ocean basin on Earth was identified within the last dozen or so years, because somebody finally put moorings in the right Polynya, which raises the obvious question about the 5th. Antarctica has a coastline of roughly 11,000 miles, much of it fringed by ice shelves, much of it accessible only in a short summer window, with dozens of coastal polynyas of varying size, most of which have never had a mooring in them for a full winter. The formation happens in winter, at the seafloor, under sea ice, at the base of the continental slope, in a place with hurricane-force wind above it. Every constraint stacks against observing it directly, and the export pathways are equally uncertain, because dense water leaving the shelf has to find a route down, and those routes are canyons and troughs cut into the continental slope, and the bathymetry of the Antarctic continental slope is, in large stretches, the gravity-derived model we discussed, rather than a survey. So put the boundary as precisely as it can be put. We know Antarctic bottom water is contracting and warming, because repeat measurements at fixed points over 3 decades show it. And that's about as solid as observational oceanography gets. We know roughly why. We do not know the full inventory of places where it forms. We do not have continuous winter observations at any of them. We cannot yet say whether the decline is a linear response that will continue in proportion to warming, or whether the shutdown of an individual source region is a threshold event that happens abruptly when the surface freshening at that one spot crosses a limit. Those two possibilities look identical in the record so far, and they imply very different centuries. The measurement that would separate them is specific, and it's not a mystery to anybody in the field. Moored instrument arrays on the continental slope beneath every major coastal polynya. Reporting through consecutive winters, combined with a proper multi-beam survey of the slope canyons that carry the water down. Instruments that survive a winter under drifting sea ice and get recovered the following summer. Several programs are building toward this. None of them covers the coastline. That's the 20. 3 shapes never measured, 4 things measured too rarely, 3 things known but never seen, 3 things known and out of reach, 4 things measured and argued over, and 3 things measured, agreed on, and unexplained. And I'd flag one thing that runs through all of them, because it changes what the word mystery ought to mean down there. In 19 of those 20 cases, nothing anomalous has ever come back from an instrument. No reading that made no sense, no signal nobody could account for, no object where none should be. The situation is that a measurement has not been taken, and the reason it hasn't been taken is fuel, or aircraft, or a vehicle that doesn't exist yet, or a winter that ships cannot survive, or a treaty obligation to leave something undisturbed. The frontier down there is a budget line and an engineering problem. The exception is the iron meteorites, where the observation, the mechanism, and the lab result all line up, and the field has so far declined to cooperate. That one might resolve either way, and it might resolve soon. The others will fall in a fairly predictable order. Gravity models of the ice shelf cavities get replaced by real bathymetry when autonomous submarines can be left alone for a year. The blank corridors in the interior fill when long-range survey drones make inland flying cheap. The winter Southern Ocean opens up when moorings and floats stop being destroyed by drifting ice. Each of those is nearer than it sounds, and each one waits on somebody deciding to spend the money. If it were mine to spend, I know where it goes, and it goes back to that coastline. Antarctica has roughly 11,000 miles of coast. 4 places along it are known to manufacture the water that fills the bottom of every ocean basin on this planet. And the 4th of those 4 was identified only in the last dozen or so years, off Cape Darnley, by a team that put moorings somewhere nobody had thought to look. There is no principled reason to believe 4 is the final count. There is only the fact that nobody has instrumented the rest of that coast through a winter. So somewhere out there tonight, in total darkness, under a lid of sea ice, with a wind coming off the plateau at highway speed, there may well be a 5th factory, pumping cold, dense, oxygen-loaded water down the continental slope, as it has every winter for thousands of years, feeding an ocean on the other side of the world. Unnamed, unmeasured, and not on anybody's map. That's the honest edge of the thing. Not a locked door. An unvisited stretch of coast, and a mooring nobody has dropped yet. Now a favor, and a specific one. One of these got under your skin more than the rest. For me, it's the boulder beneath the Filchner Ron. A camera looked at a community of living animals for a few minutes by accident. And then the hole froze shut, and nobody has been back. A discovery that made itself unreachable again bothers me in a way the enormous sea level questions somehow do not. Yours will land somewhere else. So put it in the comments and put a decision with it. Pretend the survey budget just landed on your desk and you can close exactly one of these gaps, one, and the rest wait another 20 years. The interior bed, the cavity under the Ross, a clean, uncontaminated borehole into Vostok. Argue for your pick. The reasoning people give for choosing one gap over another tends to be sharper than the pick itself, and I'd rather see the argument than the answer. If the machinery behind all this, the gravity anomalies, the magnetotellurics, the seals carrying instruments into water no ship can enter. Is your kind of thing? Subscribing keeps it coming. A like takes a second and tells me the appetite for the hard version is real. Some summer soon, a ship is going to stop off a stretch of Antarctic coast that has never had a name attached to anything, and a winch is going to bring up an instrument that spent the whole winter alone in the dark on the continental slope. Somebody will take the memory module below deck, plug it in, and read a year of numbers that no human being has ever seen. And if the numbers say what they might say, the deepest water in 3 oceans will quietly acquire a new place of birth on a coast that until that morning was just a line on a chart,